Hello and welcome to our IRA seminar series. I have the great pleasure of introducing our distinguished speaker today, Professor Max Welling. Max is a professor at and research chair in machine learning at the University of Amsterdam. He's also a distinguished scientist and a director of the new Microsoft Research Lab in Amsterdam. And Max is a fellow at Canadian Institute of Advanced Research, CIFAR, as well as of the European Lab for Intelligent Systems, ELIS. His previous appointments include a VP of Technology at Qualcomm Technologies, a professor at UC Irvine, and postdocs under supervision of Jeff Hinton as well as Pietro Perona. Max is a chair at NeurIPS Advisory Board since 2015 and has been also program chair in 2013 and 2014. He's a recipient of the ECCV Köndering Prize and of the ICML Test of Time Award. Today, and as we all know, graph neural networks are the topic, and they have found powerful new applications in scientific computation to predict, for example, properties of molecules or the forces that act on atoms. Today, Max will report on yet another exciting application using GNNs to solve partial differential equations. And this also includes joint work done with Johannes Brandstetter and with Daniel Worrall. And so looking very much forward to this exciting new chapter in deep learning. And now without further ado, looking very much forward and handing over to you.
Thank you very much for a kind introduction. I'm super happy to be here. I first want to thank the organizers for an excellent organization coming here. I'm enjoying Vienna very much, beautiful city. The other thing I want to say is very nice to actually be here in front of actual people. I've been giving Zoom talks for 2 years. And the worst thing was a couple of weeks ago, I gave a talk for a Zoom call where after 1 minute, without me knowing, the Zoom link broke. I've been giving a 45-minute talk to a screen. And when I was asking, are there any questions, I called the person up and they said, well, we're all in a bar. We just went to the bar and have a drink. So this is certainly now I know I have an actual audience, so that's fantastic. The other thing I want to point out is, so I recently made a sort of a career move, reduced my time at the University of Amsterdam and became a distinguished scientist at Microsoft Research Amsterdam, which just started, and we are focusing on molecular simulation for sustainability and more broadly also scientific computation for sustainability. The work I'm going to describe today using deep learning to solve PDEs, and numerically solve PDEs, is also part of that. And of course, but it was started at the University of Amsterdam. And then, so these are of course the two main brains behind this institute. In particular, it's interesting that of course Johannes Brandstetter was kindly lent to University of Amsterdam on an Alice exchange. It was a wildly successful exchange, in my opinion. We wrote 3 papers together. 2 are going to appear in iClear. This iClear. So he's now also joined MSR in Amsterdam to continue his wonderful work on PDE solving. It was done in collaboration with Daniel Worrall. So Daniel was a former postdoc in MLab and then moved to Qualcomm AI Research, which is also in Amsterdam. And I think these are absolute fantastic collaborators and the main contributors to this project. I also want to mention, the acknowledgement of the paper, which say that Johannes Brandstetter thanks the Institute of Advanced Research in Artificial Intelligence and the Federal State of Upper Austria for support. And I think he used a lot of your computer resources to get the results actually that you see here. So thank you very much for that support. And he always spoke extremely highly of this institute and for all the support. So that's very good to know. So the overview of today's talk is I'll talk a little bit about PDEs and graph neural networks to get you up to speed, but I think most people are up to speed because the equations for the updates are right on the board here, so people are already into this topic. I'll then talk about how you can use neural message passing to solve PDEs. And then the next step is to say, well, can we generate more data for free in some sense by using symmetries inside a PDE? And then if I have time, I'll invert the question, which is not using machine learning to solve PDEs, but using PDEs to build deep learning algorithms. And so you see there's a very intricate connection between these two topics, which I find very fascinating. And then I will conclude. So partial differential equations are basically everywhere in the sciences. I mean, in machine learning, we like our graphical models and things like this, and maybe probabilistic programming. But in the sciences, everybody uses PDEs, right? It's basically the way to describe causal evolution of local laws of physics on a sort of typically continuous space-time. And you can use them to predict earthquakes. I actually used to live right here, which is the worst place for an actual earthquake, turns out, after I saw this movie. In health, people build simulators of the heart. Weather prediction is an obvious one, right? A huge, global scale PDEs that try to evolve the weather patterns forward in time. Galaxy collisions, where entire galaxies are being sort of evolved and sort of collide. As you see this beautiful sort of movie there. Plasma physics is another set of PDEs, and typically 6 or 5 PDEs in fields that you need to evolve forward. This is something that Johannes Brandstetter is now also involved in modeling. Airplane design, like hydrodynamics. Recently, a paper by DeepMind also on electronic structure, right? Where you try to, it's basically the Schrödinger equation that you're trying to solve to figure out what quantum mechanics is doing. It's really an NP hard problem to solve, but you can approximate it. And then you can sort of see the electron cloud move around a molecule. And also in health, trying to monitor how tumors grow. So I'll have to introduce a little bit of sort of technology today. We'll have quite a bit of equations. If you don't like equations, you just treat them as background texture. No worry about them. The usual flow of the talk should go fine without you understanding the equations. But some people really like to look at equations to see what's going on. And for you, I have sort of added these equations. But don't feel intimidated if you don't get them right away. So deep learning, of course, is built on, on this tool called convolutional neural networks. Well, of course, it's a much bigger field, but let's stay with this because so we have an input image, we have a small filter. The filter sort of is convolved over the image. You will get a filtered image. You have many of these filters, so you get a whole stack of these filtered images. Then there's typically a downscaling pooling kind of operation, which makes the filter smaller. This has the advantage of saving memory because you have to store all these things in memory if you want to train, if you do backpropagation. But also it gives them a slightly more robust sort of to small changes on the input. And you repeat that process with nonlinearities in the middle. At the end, you get a sort of a huge stack of very small images. You then you turn that into a massive sort of vector. You then apply a normal neural net, which is called an MLP, multi-layer perceptron, to it, and then you make your predictions, right? So that's the usual thing. Now what we can do is we can reinterpret the convolution as a message passing update. So this is sort of pictorially what a convolution does, right? You take a filter, you plug it, map it onto an image, you multiply all the numbers, and then you sum them up and then store the result there. Now, if you think of sort of this this pixel point here, but slice it through all these channels, you'll get a vector, right? And so let's call this vector here this H1. And basically what happens here is you're going to take all these neighboring vectors, multiply them by a matrix, a different matrix for every direction, right? Because the direction is unambiguous. You always know north and south and east and west because your image is also going in a particular orientation. So these can be different matrices. You multiply this feature vector by this matrix. Then you add, you do the same for yourself. So you also multiply your own feature vector by a matrix. Then you add everything up. and then you typically push it through a nonlinearity, and then you store it at the next level. Okay. Now the problem is that in a graph, the structure isn't as neat as this, because in a graph it could be like this, and this is just one way to lay out the nodes in a graph. I could take this node and move it here, and it will be just perfectly fine. It will be the same graph. Neighbor, a node might have different numbers of neighbors, right? And so doing this trick where everybody can send their own message doesn't really work, because it now depends on the ordering. If I go, this, it will get a different result. So the easiest trick to solve this is by using the same matrix. So everybody sends the same matrix, and then maybe divide by the number of neighbors. You get something that you can apply for any graph, for any number of neighbors, in any order you treat the neighbors. So that's basically the basic idea of a graph neural net, the thing that Thomas Kipp introduced in 2016. Of course, graph neural nets are older than that. And a slight generalization of that is this sort of GNN, message passing update, which you find here, and this is the equation that's on the board here. So you have these features H, which are the things that you live on a node. It's a vector that lives on a node, and that we're going to transform layer by layer. And a message passing update first takes two nodes that are connected by an edge. Then there may also be some static information, like the distance of this node or something like this. And then you push this through some nonlinear function, like a neural net perhaps, to get a message. That's the message, for one node going to the other node. So that doesn't have to be linear. Like here it's linear, but here it doesn't have to be linear. That's already a generalization. And this can depend on both I and j, where here it only depended on j. Then the next step is to collect all the messages to the central node, which is exactly what we did here, right? We collect all the messages, sum them, which is also permutation invariant. And then on the node, we do another nonlinear function where we take this sort of aggregated message, some information living on that node, and the actual feature value at that node, push through a nonlinearity and get the next level sort of feature vector. And you repeat this many times, and then you backpropagate it, and you get basically a graph neural net. There's one sophistication of this that is typically important. Actually, for the work today, it's not yet important because we haven't been able to figure out precisely how to do it. But with all the stuff that we did for molecular simulations, it is actually very important. And that is to make them also equivariant under rotations. Because if I have a molecule, let's say, and I rotate it, any prediction I make, like the energy levels of that molecule, shouldn't really change if I rotate it or move it in space. So what we want in equivariance is to say, well, let's say I have some graph, and in that graph I have scalar features, which are the sort of histogram here, things that don't transform under rotations. And I have some vectors, which are things that do transform under rotations in the way that we intuitively know how they change. And then there's, of course, the positions, which is also some kind of vector, right? Now, if I rotate this object, like I did here, right? So this moved here. Now, these things don't change because they are scalars. This vector, though, did rotate, as you can see, in the way you expect it, right? And now what I want is if I first transform it, which is I transform the positions and the vectors and the scalars, everything transforms under a graph neural net update, and then rotate, it should give me the same result as first rotate and then transform. That's called typical equivariance. That's what we want, which the end result will be that whatever I predict, whether it being a scalar quantity like energy or a vector quantity like forces, will all transform properly under rotations. And again, so here's the updates. I won't really go through them. You can read them if you like at home, but it's a variant of what's on the board, which is also has, for instance, these differences, so that you can also understand, if this atom is a certain distance from that atom, you can take that distance into account when you do these updates. And there's these vector quantities which are also updated in an equivariant way. Okay, so there's further reading. So I just wanted to highlight this because so in this work, so these are more sophisticated versions of graph neural networks that are equivariant under these sort of rotations and translations. This one has Daniel Worrall on it. And this is the later one. This is the first paper that we did with Johannes Brandstetter. Very beautiful paper on steerable equivariant message passing on molecular graphs. I can highly recommend it. So when you can see this beautiful illustration of sort of these representations that are living on these nodes that are transforming as you go through the layers of a neural network. And this has this property that if you rotate your head and input the data in a rotated version, you'll see exactly the same thing happening, but then rotated. So this thing is beautifully equivariant, more general than the one that I just described, more powerful. Okay, back to PDEs. So of course, this is a massive area, right? I mean, it's like PDEs have been there for so many years, hundreds of years, I would say. And many books have been written on it. So, how are we going to make a contribution to this, not knowing anything about PDEs really, right? Of course, it's the arrogance of the machine learner. Let's see if we can do something with deep learning and see where we go. Now, there's a huge list of things that these PDE solvers need to be able to do. They need to be accurate. They need to be stable over long rollouts. They need to be fast. They need to have, for instance, speed is important if you, let's say, want to control a plasma, right? You want to have very fast prediction because otherwise you don't have time to control, let's say, with a magnetic field, the plasma. You don't want the computational cost to be too high. You want it to be easy to use. You would like uncertainty quantification. It needs to generalize across different initial conditions, right? You don't want a separate solver for every initial conditions, obviously. Different boundary conditions, PDE parameters, maybe. If you change the PDE a little bit, you still want to use the same numerical solver. Maybe the integration grid, you should be able to change, especially as the boundaries are different. Integration grid regularity, which is not just the resolution, but also the regularity of that grid. You could have an irregular grid. The geometry of the problem, maybe it's a plane, but maybe it's the inside of a torus for a fusion problem. The topology, this actually the geometry, it could live on a flat space and a curved space. The topology, which could be a torus or a plane, whatever, and then the dimensionality of the problem. So all these things need to go into these solvers, and they did. And there's therefore many, many solvers around that are highly specialized for certain equations. That's what we call a splitter field. For every new PDE, somebody designs a new, really good solver. They're very good. They often come with sort of error guarantees, which is very important, but they're also very expensive to run. So in order to run them forward, it really takes quite a bit of computation. So what we are doing in machine learning is sort of amortization, which I call it, right? Which is, in some sense, it's a recycling economy, which is you're doing a lot of computations, but you're not throwing away those computations. You're storing them as a data set. You're looking at patterns of previous solved problems, and you're trying to learn new solvers to sort of satisfy, to do better when it sees certain patterns arise, right? So it's an amortization, and that's what we're going to develop now. That's the original idea, and of course there's a whole field. Even before we were in this, there were people already doing things like this, but it is very early days and it's very exciting area. So, and the progress is fast, I think. So, there are many classical solvers. I mean, I just listed here a few, grids and cells, methods of lines, finite differences methods, finite volumes. I mean, there's a huge list of these things, right? And I don't actually know much about it, so I'm not going to dwell on it. So the more recent ones, which are we call neural PDE solvers, so trying to use machine learning to solve things, they fall into sort of two categories, perhaps. The neural operator methods, and here's sort of the neural operator methods idea. So it's a mapping from an initial state, the initial condition, and time, which is the time at which you would like to predict something. So here's your initial state, and then there's an operator machine learning method that then tries to predict at that particular time what the solution looks like. And you separately do this for every point in time, right? So for every point in time, you have a prediction for what the solution would look like. There's also autoregressive methods, which are indicated here, which is you sort of do this iteratively. You take a slice of time, you then predict the next time point, or maybe the next few time points. And then you take in, this new predicted thing. And from this new predicted thing, and maybe the entire past, you then predict the next time point. So you use whatever you predicted as input again, to the new prediction, much like an LSTM, right, or an RNN or something like this. Okay, so that's an autoregressive method. There is been quite successful instances of both of these methods. So the one that got a lot of attention is this Fourier neural operator, or Fourier neural operator, which is of the sort of neural operator kind, where you take your input vector, you do a Fourier transform on the input vector, on the spatial part of the sort of the input, you do a Fourier transform, and then you do some transformation on the modes. Typically, you're throwing away the high frequencies and maybe mix the low frequencies in some sense, and you do an inverse Fourier transform. At the same time, you also do typically a pointwise convolution, which is basically you mix the channels together, and then you add those things up, and then you get the output, and you repeat. And that's and then you predict some point in the future how the solution looks like. So this is a very good way to solve these equations. It's remarkably successful. And an example of an autoregressive method here is this paper, Barsinai et al., where they really tried to predict the derivatives that you need in a PDE. You need spatial derivatives, and you need to approximate them by finite differences. And you typically do this with a stencil, which is basically some weight vector which says, your left neighbor -1, your right neighbor -1, your current state +1, and then you get some kind of derivative operator. But you can either use one that makes sense mathematically, or you can learn it. And the beauty is that they learned it. So this is a Berger's equation solution, which creates these shock waves, very sharp discontinuities. And they found that, these stencils, which approximate these derivatives, actually change depending on where you are in this thing. So close to this shock wave, you should use different stencils to approximate these derivatives than when you're in a sort of more regular space. And so that's an early example of an autoregressive method where you just stick that thing, this learned stencil, into a usual solver that solves the equation over time, which is an autoregressive method. And that was one of the earlier papers, and also quite successful. Okay, so now a little bit more detail on a PDE. So PDE basically has a bunch of fields, U. Could be higher dimensional, right? Could be 5 fields or something like this. And this is the time derivative of that field. And it connects it to some function of time, position, field variables, and all of the spatial derivatives of those field variables. If you have a higher order sort of time derivatives, you can always rewrite it in, by redefining the derivative of something as another field. You can always turn it into this kind of first order in time PDE. There is an initial condition, which is the U given at time 0 in all space. That's your initial condition. There's boundary conditions, which tells typically something like the value of the field at the boundary should be 0 or some value, or the derivative, orthogonal to the boundary should have a certain value or something like that. And well, that's the domain. Okay, so that specifies it. Once specified, the solution is unique. So that's good. And then there's a bunch of special cases, and the examples that we will show are of this special case, which is this shape. You can write it in this shape, where sort of this function can be written as the divergence of a flux. And using Gauss-Bonnet theorem, basically what you can show is that it basically means that the change of stuff inside a volume is given by the difference between what's flowing in and what's flowing out, which seems to make a lot of sense. Like the amount of stuff in the system should not increase or decrease, basically saying there's no sources or sinks in this system. Things just flow and move around, but nothing disappears or nothing is created out of nothing. You can write those as that. Okay, so now this is maybe the one that has the most equations on it. And this is how would you train a PDE solver. Okay, so it is somewhat core to the talk. So the first thing, of course, you need to do is you generate data from a classical solver. And this is somehow turns a little bit into a chicken and egg problem, because if you have data for a particular PDE, if you have to generate it from an ordinary solver, why would you train something because you already have the solution, right? This feels a bit ridiculous. However, the trick is that you can generalize to new initial conditions, new boundary conditions, you know, perhaps even new PDEs with slightly different parameters. So the trick is in the generalization to new context. Now there's two parts which look very similar in the objective function. Now let's forget this for a moment. Let's just focus on this. So k is the time. This is autoregressive method. So k is time. Now we have some data from a traditional solver. And so let's say I have UK from a traditional solver and UK plus 1 from a traditional solver, right? So one slice solution, another slice solution. I want to train an operator A that maps the solution at some time to the solution at the next time, right? That's my operator A, and that has all the parameters that I'm trying to learn. I have some loss which measures the difference between these two things, which I want to make small. And then I want to sort of say, okay, I need solutions from a PDE from some distribution PK, basically meaning, you know, you have some, you sample some initial conditions and you solve this thing, and then you get some solutions UK. And then this is basically running the solver one time step in the future, which is, you know, typically deterministic. And then you sample some time slices in that system. Okay, so far so good. But there is a problem, which is the stability of the solver, which is basically the core problem, which means that as you start to integrate, it's starting to make small errors, and these errors are going to accumulate, and then it's going off track and just goes into a wild direction, right? And you want to suppress that behavior as much as possible. So the way we suppress it is by saying, well, let's first evolve the solver a little bit, including the errors that it's making. So now I have some kind of noisy, you know, solution. And then I'm asking it to predict the correct thing again from this noisy solution. So if it's going off track, I'm going to ask, correct yourself back to the true solution, right? So I'm going to first evolve and then ask it to predict back. So this epsilon is this thing that's the noise that are the integration errors after a certain amount of integration. It's basically saying that, you know, this UK plus epsilon is the actual propagated solution from the neural PDE solver. Now, if you ask it to do this, it has the tendency to try to correct back to the true solution. And you know, and in detail, it's very easy to implement, because it basically means that you first predict forward, right? And then you predict forward again, but then you only try to optimize this part. You only try to say from this noisy solution, predict the true thing, and don't back propagate all the way back to the beginning. Yes, Sepp, go ahead.
Do you hear me? Oh, you
Yes.
hear me. In this epsilon is the whole history U1, U2, U3 contained. Do you know how it goes off to track, or you are some like Gauss off track epsilon?
Yeah, so it's not Gauss, because and that actually works surprisingly bad. If you use just random noise, actually goes worse. So this, you should really think of this epsilon as the difference between, you know, the actual correct solution and the solution you get by propagating your neural operator into the future.
Since epsilon has also old values somehow.
Yeah,
okay.
It's in it, but you don't actually propagate through it, right? So you forget this information. You're just trying to figure out, how do I get from this noisy thing to the correct thing?
I like it, because then you have the right noise distribution automatically.
And that was Johannes' idea, which actually made a big improvement, which is really good. And here's another idea, which is temporal bundling. It's sort of sitting somewhere between, you know, neural operator and autoregressive, which is saying that you start, instead of trying to predict one time slice in the future, you're trying to predict, you know, a whole bunch of time slices into the future, and then autoregressively go forward from there. So it's in between neural operator and autoregressive, sort of autoregresses over a longer future. Okay, so then now some detail on the actual model. Okay, again, this looks complicated, but I'll sort of unpack it. The solver has this structure of an encoder, processor, decoder. And then you repeat it because this thing predicts sort of, let's say, 10 time slices into the future, right? And then you repeat this thing again. So 10 time slices into the future and we repeat. Okay, the first thing we do is we have our input. I guess the equations are not quite here yet. Let's see if I have them here. Oh, the equations are not here. See if I have them here somewhere. Yeah, okay, so here are the equations. Let me just look at these equations quickly. So, oh, sorry, it's coming. Oh, sorry, I'm going too fast. Right, okay, so this is the entire, architecture. And I'll just go through these things one by one. So the first thing, it takes the initial information, the fields and the positions and everything that you have. It maps it onto feature vectors that go onto the integration grid. So this is an irregular integration grid that is modeled as a graph, right? So every point is a point in space that sort of talks to its neighbors and trying to do the integration. We do a graph neural network updates on that thing to sort of predict time slices into the future. And then we do some additional smoothing over time to get the solution smoother and sort of correct itself a little bit. So the last part sort of takes a node and over time sort of does a little convolution to it. But I'll go over these things one by one. The things that the variables that we have to keep track of are location, xi, the fields, you know, at variable xi, so position xi at time k. And then on the graph neural net, we have the feature vectors at position I and sort of intermediate time m, the thing that we want to predict in the future, layer m. And then there's the parameters of the PDE itself, which define the PDE, but for instance, also the boundary conditions. Okay, so first a little bit on the encoder. So the encoder takes in the field values at some history. So this basically says k minus, you know, k times k. So basically it tells you k time steps into the past. We are going to take the history of these fields. We're going to take the position. We're going to take the time, and we're going to take the parameters and the boundary conditions and whatever of the actual problem. We're going to push it through a neural network, epsilon, to get our initial features, which we're going to map on the graph neural net, on the nodes of the graph neural net. Okay, that's what you can call an embedding, right? An embedding of your original problem. Okay, so then we'll have this sort of graph neural net update. So this is exactly a version of the graph updates that I showed before and that are on the board here, which is basically I have my feature vector at layer m, which is time slice m, at position I and j. I have, you know, my fields. Actually, we use the differences of these fields here. It doesn't have to be, but in this case, we use the differences of the fields at node I and j. The difference of the positions, because we know, oh, it's hard to see, I see, sorry. So the difference between the positions, because we know the problem is sort of translation invariant, so we only let it depend on the difference between these things, and then the parameters theta of the PDE. So that's the message, and then we do the typical thing is we collect the messages, we sum them over the neighbors, and we push them through another nonlinearity psi using the features f to get the next feature f at that node, and then we repeat. So this is just another graph neural network update, you know, which also includes in this case these fields u. And then the final thing is decoding. So we now have these solutions on every node f. So let's say the feature values on node I at time slice, you know, m. And then we do basically a convolution, the same convolution for every node. We convolve it a bit to sort of smooth the solution out, so to make it a little smoother over time. That will give out these d vectors, and then we do an update on our fields u by basically, you know, updating the current value with the difference d multiplied by the time difference. So this is just an update of your fields. And now we have the new value of our fields over, a number of time slices into the future. And then we repeat. We go back to the beginning and we do another set of this to get the next set of 10 updates of you into the future. So that's the decoder part. Okay, so that's the architecture and the learning algorithm. That's it, basically, right? So a GNN with some additional bells and whistles and some smart sort of learning objective to make this tick. So we'll be looking at first at this one-dimensional PDE, which is basically a mix of Burger's equation, Korteweg-de Vries equation, but also heat equation are in this. And it has sort of the time derivative here, and then it has this, nonlinear term, which is a first order derivative. Here's a second order derivative, linear, and even a third order derivative. So the Korteweg-de Vries has these third order derivatives. It has these soliton solutions. Initial condition, where this delta is given by this thing, and that's sort of a forcing term. That's sort of a periodic forcing term that drives the equation forward. The discretization grid, we typically have 250 time points, and then we have a variable number of space points, so either 150 or 40, and then we create ground truth by this sophisticated method. We know 5 that produces ground truth for us. So here's some solutions. So this one is to be interpreted on the x-axis. We have space. These are the field values, and then the coloring is time. So you start with the blue solution, right? And you create at the end the red solution, and you see this formation of what's called a shock wave. It's a very fast transition from a large value to a small value, right? And then, so this is ground truth created by this Vino5 scheme. This is sort of a high resolution integration grid with a neural procedure. And then you see that if you actually go down in resolution, this thing is actually amazingly stable, right? Only at 40, it still creates the shock wave, which is interesting. Well, you do see this problem of course, exploding errors. So here it's a difference. So this is space, but now here is time, and the coloring is now this, the value of the field, right? And you see in the beginning at small time slices, this is ground truth, and here you again have the different spatial resolutions. You do see that in the beginning it's good, but as you go, to higher time sizes, the solutions really start to differ from each other, meaning that you get this accumulation of errors effect. So here we generalized across different parameters, right? So it's pretty exciting. You sort of train your neural method on one PDE, and then you hope it will actually work well on another PDE with different parameters, which I think is very interesting. So let's focus on this one here. So here we have sort of the baseline method, which is, let's say, Vino5 scheme with different resolutions again. Right, so that's sort of the ground. So this is the the high resolution ground truth, but here sort of you run a method with a smaller resolution, and this is the neural version, trained version on different resolutions. It's never seen this PDE, but it's certainly better at understanding. It's in generalizing to this kind of weird effect that's happening here, these oscillations here. It understands that it needs to create these oscillations even at low values of a resolution. So I think it's very promising. And in fact, my dream is that it could open the door for actually learning the PDEs completely from data. You just give me a bunch of data, and you just not only train your PDE solver, you also train the parameters of your PDE, and it just tells you this is your PDE and this is how to solve it just from data. Here's a two-dimensional example. It's a Navier-Stokes solution, just to show that it doesn't work in one solution, but it can also go to two solutions, two dimensions. The problem is, of course, that if you go to very high dimensions, it gets increasingly hard to do these things, right? And so that's something, even 5 dimensions is very challenging. And that's an open field, I think, how to use machine learning to do that. Okay, so then the next topic I wanted to talk about is symmetries, because one problem is that actually the generation of the data is very expensive, right? Is what I said is that, I mean, it's sort of a chicken and egg problem. You start with an expensive solver. Then if you have to first generate a huge amount of data with a very expensive method in order to be able to train your method, it's not really practical. So it's very useful to come up with a method that creates sort of data for free very cheaply. And it turns out you can do it because these PDEs have symmetries in them. And a symmetry, basically, I'm just going to try to explain what a symmetry is with a bit of math, but maybe intuitively, it's just that if you take some, well, let's just first do this one here. So here's intuitively, here's some solution of sort of a Korteweg de Vries equation, right? This is the solution. These are solitons, which are moving in space. So these sort of stable sort of things. Now you can transform the solution using some transformation. The transformation are actually written out here. So these are, this is a time shift, this is a space shift, this is a Galilean boost, where you change the space, but also the field value. And then there's this scaling operation. And there's another one which is cannot be written in this convenient form, where you take two solutions and you can combine them into a new solution, which is a different kind of symmetry. Right? And here you can basically see if this is a solution, then 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 this is a solution. And you can sort of generate them almost for free, because you just transform your previous solution into a new solution. But it does create a new data point for your learner to learn from. And this is very similar to what people do in image recognition, right? They take an image and they maybe mirror the image, or they rotate the image or whatever, and then they feed it into the learning algorithm, and that helps a lot, right? Of course, my dream is to make the actual algorithm equivariant to these symmetries, so you don't have to feed them as data, but that turned out to be a little harder than we thought. Okay, so in order to define what a symmetry is a little bit more mathematically, you sort of create this what's called prolongation of your field, which is basically the field and all its higher order derivatives, all the derivatives that you need to describe your PDE, right? So for instance, here for this heat equation, you have the first time derivative and the second spatial derivative. So a solution to a PDE is basically saying some function, typically a linear function, but can also be a nonlinear function, of x and this prolongation vector has to be 0. So if you write all these derivatives basically and x, then you can write this sort of linear combination or nonlinear combination of these things and set it to 0, and that just describes your PDE, right? So here it's ut minus alpha, second derivative is 0, so it's a linear combination of these objects. That describes your PDE, and that's what you need to solve. Of course, there's also boundary conditions and things like this. Okay, so then a pointwise transformation basically tells you I'm going to change simultaneously x and my field variables at x in some particular way, such that so x goes to gx and u goes to gu. So you change them in some particular way. I'll have an example in a minute, such that if my PDE holds for the original things, then the same thing where I've transformed x and u will also be 0. So you map one thing which is 0 to something else that 0 satisfies the PDE equation. All right, so here's an example. So this is the Korteweg de Vries equation. It's nonlinear here because it has this term. It has third order derivatives in it in one dimension, periodic boundary conditions. And then you can have these 4 symmetries plus this other weird symmetry that I mentioned, which combines 2 solutions. And then basically what you can do is you can say any group element can be written as the product of these 4 things for some values of epsilon. And so I can create transformations of my original solution. So data augmentation then works as follows. First, you find all your symmetries of the PDE. Now, it turns out there are programs out there that can do this for you. Or you can just stick in your PDE, and then it will deliver all the symmetries of your solution. So that's very handy. It's been done a long time ago. So then you sample some epsilon, which is a parameter value for that group element, and there you create your actual matrix that transforms it with that value of epsilon, and then you take the product of all of these matrices together to get yourself this group element. That's your transformation. Then you transform X and U to GX and GU, right? And then there is this final step that you're on a grid and you have to map things back on a grid. So an example here, here's your original, say, solution. These are the points on your grid. Then the symmetry is X goes to X plus epsilon U. So that's just shifting the points to the right. So you see that every point shifts to the right here, right? So every point is just shift to the right. Then the new points you just interpolate again, a new function, right? And then you sample that new function at the original points X that you had, and that gives you U prime at those original points X, right? So then you have a solution that UX goes to U prime X, which is your transformation, and you stick that into your as a new data point in your solver. Okay, so then some results to show that this really works. So we're looking at these three equations here. It's in one dimension, and there's a bunch of methods that Johannes compared, which is the Fourier neural operator and the autoregressive methods. So on the first graph, what we see is here the number of training examples that we increase, and here's the error. And then this means no data augmentation, and G means plus data augmentation. And you see that sort of the error comes down. Let's say for this one, for instance, which is no, this is Kuramoto-Shivashinsky. You see that you sort of get a shift down in error if you do data augmentation. For this one, the blue one, which is Korteweg de Vries, you get a bigger shift. And this one, amazingly, Burger's equation, the slope changes. And that's probably true because it has this sort of, this, you can combine two equations into one new equation. Here we see that it both works for Fourier neural operator and ResNet solvers. So the same phenomenon happens across different methods. Here you see that it helps for both neural operators and autoregressive models. Funny enough, the autoregressive models have some non-polynomial behavior. It goes faster, towards more samples. And then here you see the impact of the different transformations. And some transformations don't do a lot, typically translations in space, because we already had modeled, a translation invariant. Translation variance was already modeled in the solver, so it didn't add much if we were doing data augmentation. Others had a very big impact. So here you see some solutions, a rollout over time this is space and this is time. Now, it's just very hard to see the differences between them. So if you look at the actual errors, you see that with more samples, this does, if you do augmentations versus no augmentation, the augmented version really has less issues with sort of exploding errors if you have a sufficient number of samples that you use. So here you see the same phenomenon, time and error, right? And the methods which do not do data augmentation, which are here, they have the errors accumulate faster, and this is a log scale, than the method where you do the data augmentation, right? And it's important to know that this data augmentation is almost free, right? So it really has a big impact on your solution. And then the last part, I'll just go very fast, is sort of the idea that you can actually reverse this idea of machine learning for PDE solving, but maybe PDEs are have a deeper connection to deep learning than just as a solver. And the idea is here, this actually work with Mark Finzi and Roberto Bondeson, is that you can actually describe the linear layer of a convolutional neural network with a PDE. And so you can write sort of, as you go through the layers of a neural net, the convolution, you can sort of make that a continuous, instead of just a one-step thing, you can just integrate it continuously. And you can describe this as a PDE. And the advantage is that you can now work on an arbitrary grid, because you're basically thinking of this as a continuous signal that gets subsampled on a grid. And it's independent of the actual grid, because we're just thinking about the original solution. So the way we do it is we take the points, we fit a Gaussian process to the points. So here we have the input, we fit the Gaussian process, and then we have some operator which is given by a PDE that we sort of evolve forward. The Gaussian process is being evolved forward, and then we make a prediction. Well, I mean, let's skip quickly go over the equations, but you know, so the operator that you need in this PDE is a shift operator, which is what you would normally have in a normal convolutional neural net. And in addition, you have this blurring operator, which is diffusion, which is new in some sense because it blurs the solution. It doesn't just shift or transform the solution, it actually blurs the solution. And then there is an operator which combines a whole bunch of these things together using weights. And then you can show that acting with this operator on a function will actually look like a convolution. And of course, that's exactly what we usually do, a convolution. So, I mean, this might have gone a little fast. The main point that I want to say is that you can think of the linear layer in a convolutional neural network as solving as the solution of a PDE. And then you can generalize, for instance, by adding higher order derivatives and adding blurring terms. Okay, so then I'll conclude. I would think that PDEs are, you know, in the actual natural sciences are perhaps the most important modeling tool that people have. Basically, everybody in the sciences uses PDEs or ODEs to describe their phenomena. And what I'm thinking is we are seeing an early disruption in this field of solving these PDEs using deep learning. And of course, the idea is to learn the patterns that you see in previous you've been solving this thing for a while, and the human process is to look at these things and then be very smart about, oh, well, in this particular case, I should use this, in this particular case, I should use this, which is just pattern matching, right? It's just trying to be smart about, you know, which PDE needs which solver. The idea about machine learning is to automate all of that, right? To basically say, I'm not going to rely on humans over the years to do this pattern matching. I'm going to try to learn these patterns and then integrate them into the solvers. And of course, you can do it completely neural, which is throw away everything we knew about neural solving and just doing everything neural, or we can have more hybrid methods where they have some parameters, some settings of these algorithms, maybe just which algorithm we should use at which time to use with machine learning. But I think there's going to be a disruption in this field because this is an incredibly important application area. It impacts lots and lots of fields, and we are seeing fast progress at this point. So I think we'll see, just like in computer vision, where everybody's doing deep learning now, it could well be that in this field, everybody will start doing deep learning to solve their PDEs. I've also argued that there may be a deeper connection in the sense that we can actually maybe view deep learning as a sort of a PDE itself, which is intriguing, I think, because it might sort of create synergy in two directions. And the hope is, of course, that these tools will help us predict complex physical phenomena much better. Here's a beautiful example of this paper, ForecastNet, which is run by NVIDIA, I think, or at least sponsored by NVIDIA, where they take a global model of the entire Earth and they're trying to predict, so it's ground truth, and they're trying to predict, you know, oh, here's the truth for an inset. This is initial condition, so this has to be mapped to this, and this is the actual neural operator. So this is the actual future measurement, right? And so here you're trying to predict these cyclones, and it's quite good at predicting, let's say, from this picture, you know, these sine clones. So these methods can have a huge impact on, for instance, predicting where storms will happen and things like that, right? Yeah, and there's you know, here's a bunch of other applications that are already mentioned, and I think it's a very exciting field to put more effort in. I'll end there. Thank you very much.
Excellent. Okay. Thank you so much, Max. And I think there's already quite a few questions. Let's maybe get started with some first 1 or 2 questions from the online audience, and then start mixing between the room and on. A very first, in a way, maybe basic, but still valid question is on the slide training a neural PDE solver. How do you know the correct solution?
Yeah. So the correct solution is given by. I mean, if you have like this weather thing, you actually know the future at some point. So that would be actual measurement, right? And the other way is to actually, let's see, where did I talk about this? Here. So the other way is to take an expensive solver that is out there to create this data set for you. So you basically, that's your teacher. So the teacher is some expensive solver. You look at do its thing, then you figure out what the patterns are, then you freeze that into a neural net, and then the neural net can do orders of magnitude faster. I mean, we're talking about perhaps 3 orders of magnitude speed up for these methods.
So it's mostly on the speed up, and you rely on the calibration validation of the existing expensive solver in the end.
Yes, right. But of course, you can make them as precise as you want, because you can just, you know, increase the resolution. It becomes more and more expensive, but you can get more and more precise solutions this way. It's a game of computation, I think. You know, how much computation are you willing to invest in this? Yeah. Or actual measurements.
Thank you, Art. So just to add on to that question, doesn't mean that you use the train data from the classic solver, which you're limited to the accuracy of the classic solver. So your neural solver would be limited to the teacher's accuracy.
Yes. So depending on whether you use actual data, then you will be limited to the resolution of your data or your measurement, or you're limited by the resolution of your solver, right? But then for the solver, you have an actual knob. You can turn the knob to the right. You just pay in terms of computation.
Another question I had, sorry, it's also related to this, is that with classic solver, you kind of know that, or there is some guarantee to the error.
Yeah.
But with this neural solver, how do you know that, especially for the unseen conditions, how do you know that it's not going to be completely wrong?
Yes.
Is there any guarantee there?
No. And so this is somewhat of the issue with deep learning in general, right? You know, there's a trade-off between having guarantees. So for instance, for, you know, kernel methods, we had beautiful guarantees, but not very accurate solutions. And for deep learning, we have more accurate solutions, but we have to let go of the guarantees. And I agree, this is a downside of this, right? So if you need your guarantees, you probably want to stay with a sort of more classical solver, or somebody really smart needs to come up with actual guarantees for this, right? The intermediate way would be to train a separate network to detect whether things are going wrong, right? So you can have an uncertainty prediction algorithm that tries to detect whether, you know, the solver is going wrong. But then, of course, that one can also have an error, and you might not be able to monitor that error. So, you know, there's always some hierarchy at some point that, you're stuck with. So, so I don't think there's no sort of formal verification of this error of some kind, you know, that this will always, you know, give you the correct answer like 10 time steps into the future. You might see something new that you've never seen, right? And then things might be wrong. Similar in a self-driving car, I think, is people have the same issue, right? So you have some deep learning solution, a complicated solution. You've trained it maybe on many instances, but then you drive into Vienna, into a street that has never seen, something strange happens, and, you know, this thing might go haywire. We see this with Tesla quite a bit, I think, at least in the news.
Yeah, thank you for the talk. I also have a question, and I wanted also a question about the generalization. And I wanted to know if you take any specific steps to facilitate generalization in maybe the architecture, if there anything you do so that it can generalize more easily to unseen equations.
Oh, yeah, okay. Well, this is in some sense some robustness to generalization, but yeah, but you're asking more towards, so for instance, in this example, so in this example, we actually do train on the different values of alpha, beta, and gamma. So we sample values of alpha, beta, and gamma. We then train our solver to on these different values. And then we say, now take a new value and then generalize to this new value. So in some sense, you're trying to sample the domains as best as you can, and so that it sort of interpolates between domains and doesn't have to extrapolate, because I think extrapolation is very difficult.
Yeah.
Otherwise, yeah, I think there's probably more that can be done, right? So I think the other one is, of course, boundary conditions and initial conditions. We also sample those. The symmetries, in some sense, is also trying to be robust to more transformations of your data. So mostly it's trying to get data of some kind to cover the space.
Yeah.
But otherwise, yeah, I think this field is wide open. So I think more interesting things can be done, certainly. Yeah.
I have a related question. I mean, two parts of your presentation where one was data augmentation and the other improvement of the architecture. So my question is, as I understood it, so in the short run, the symmetries, you said you easily get the symmetries. In the short run, I assume it would be the best to use them to make improvements. And what about the long run? If you change the boundary conditions and other PDE parameters to a greater extent, would you think that the improvement of the architecture would still be better, or is it, what's the path to go? That's the main question there.
Yeah, so these are sort of two slightly orthogonal directions, right? And so one is really trying to get more data. And, if I mean, ideally, I would like to actually not have to use it to create more data, but I would like to embed that symmetry into the solver itself using an equivariance neural network.
Because of data efficiency, or is it even better generalized than the architecture?
Better generalized, because if you know the symmetry and you bake it into your neural net, you sort of have in one shot, looked at all possible data augmentations, right? Because the thing is guaranteed to give the right answer for any of those transformations. So that's sort of how data and model do interact a little bit. If you have a really good inductive bias, there's two ways. You can either bake it into your model, or you can try to generate more data so that the model can learn this bias, right? I'd rather put it into the model directly than by data augmentation.
So with these symmetries, we don't get enough to make this still possible with the symmetries we use.
Sorry, this still?
Why are the symmetries not enough to achieve this goal?
Yeah, so the issue is we haven't really gotten to the point that we know how to build these symmetries into the neural net. It's not the same as we did before with Equivariance. It's slightly more complicated, but I think it can still be done. I'm not sure we will be the first one to do it, but I think somebody will come up with a solution. It's a very interesting area, I think.
Max, thanks for this talk. It was a great talk. I think everybody is excited about this field now. I have perhaps a higher level question, because there's a lot going on with Fourier neural operators.
Yeah.
But should it be restricted to Fourier? Because I like the idea. You look at the data or it's a problem from a different point of view in the Fourier space.
Yeah.
But there are other transformations like radon transformation, where you go along lines.
Yeah.
Do you think there will come up architectures where you have the Fourier path, the radon path, the original path? Because I think to look at the same problem in different spaces, transformations, makes a lot of sense.
Yeah.
What is your take on that?
Well, it's a great question. Of course, I mean, let's first reason why this works so well. So the graph neural net operates very locally. So it looks at its neighbors, and the PDE is a local thing, so that intuitively is the correct thing to do. Actually, these solvers also solve things locally. But there might be global patterns. And the Fourier operator sort of, I think, leverages these global patterns. It sees these global patterns. If there's periodicity somehow, it sees them and it can sort of propagate sort of this global pattern much quicker. And so it also has this smoothing effect because it removes all the high frequencies. Now, that's on a two-dimensional plane. If sort of a two-dimensional Fourier transformation makes a lot of sense. If, you know, let's say you're in a tokamak, maybe that's not the right thing to do, and maybe there you need some kind of other type of harmonic transformation. Or on a sphere, you might use spherical harmonics, for instance, right? So it has to do with the topology or the geometry of your space, certainly. But even beyond that, it might actually be quite interesting to think about, instead of local transformations, to just try to parameterize more global transformations and use those, or just use a whole library of things that you know and just try them out, all of them, right, and see which one works, which one sticks. So yeah, so these are certainly, you know, this was a bit of a surprise why this works so well, and people now also use it in computer vision, and it seems to be a good idea. So yeah.
I think there's a somewhat related, and somewhat you already answered that question, because the authors of the paper seems to also have been using GNNs according to Aras Paco, and got worse results. So is there a certain class of PDEs, and is there also a class of PDEs where you expect good results?
Yeah. So for this, you need somewhat of a regular grid, right? And so this works well if you can sort of sample your space regularly and sort of on a regular grid. I do believe that if you so this is superior in this case to a graph neural net. However, you know, the graph neural net shines if you need an irregular sampling of your input space, or if your boundary conditions are complicated. You know, so it is a more flexible tool in that sense. And of course, now the question, you know, back to sort of Seb's question is, you know, could you even on an irregular grid come up with something that looks like a Fourier transformation to combine these two things? And I think there are, you know, Fourier transformations you can do on irregular grids. They do exist. And so that could be a step to be tried, right?
Yeah. I have, sorry.
Michael, you go ahead.
Sure. Okay, sorry about that. I have two short questions. One is an understanding question. I mean, could you learn that grid to interpolate? So
Yeah.
maybe as a pre-step or as a combined step, because that would be a great advantage.
Yes.
Right?
So we've discussed this many times, and I think the only reason we've not done it because we haven't had time to do it. But
okay.
It seems you could just very easily backpropagate to the actual positions of this grid, right? So here, you know, where to place these, so the values of xi, you can just backpropagate to those positions and move them in a position where, you know, this resolution is needed. I don't see any principal reason why this wouldn't work.
Okay. And my second question, I really like your work, and again, thank you very much for a great talk. You mentioned that maybe this could be a start of a paradigm shift.
Yeah.
That would be fantastic. If I look, and you compared it to vision, there you had sample data sets. There were sample, how shall I put this, marquee kind of things that everyone could compare each other themselves to. So there were benchmarks. Would it be a good idea to create a benchmark? Are there benchmarks? What should we do? How should we value them? Yeah.
Oh, absolutely. We should, you know, this field is not as mature, and maybe the next step is to create these benchmarks and competitions. But there's a lot of data, right? I mean, there's a lot of weather data out there, right? You know, years and years of, you know, actual weather patterns that are being measured. And so, but there's also lots of Navier-Stokes solutions out there that people have computed, and hydrodynamics, and there's a huge data sets that can be created. And I completely agree that at some point, you know, this is the phase where everybody throws in their algorithm, say I'm best, right? But it's not quite clear really under what conditions you're best, and, you know, are you really best in the first place? this is just an exciting new start where all your papers get accepted, which is also good. But then there comes the phase where people start become more rigorous, right? And that's what we need now. We need data sets and metrics, clear metrics of how to measure the error that everybody agrees on, standardized way of measuring progress. And this will happen. It's just early days, I think. Yeah.
Thank you very much.
You showed some slide where the transformation, so to say, is composed of more elementary transformations.
Yes.
So I guess in general they are not commutative.
Yes.
So how is that done? So is the order dependent on the type of PDE or on the properties of the PDE, or do you just randomly?
So this equation here,
yeah,
right? So it turns out every group can always be written under some conditions as a product of these generators in in a particular order, right? And
the order is dependent on the PDE properties, or
well, it depends on the group. So every PDE generates its own group, and every group can be written as a product of these one-dimensional things. And then you just have to come up with some convention that you like. And maybe there's not unique, probably there's multiple ones that you can write down. Come up with some convention of a product of these one-dimensional group elements, such that you can generate every G in the group. Now this is possible. Once you have set that, you can just start sampling these epsilons and start generating G's by sort of generating a little bit of this, little bit of this, little bit of this, right? And then creating your G, and then use that G to transform your input and your solution.
Thank you for the wonderful talk. So my question was, you mentioned like irregular grids. So what if you'd like to maybe increase the resolution, or like learn how to increase the resolution? I'd like your comments on that. Thanks.
Well, it's related to an earlier question about, you can sort of move these points around. Now the question becomes, can you also adaptively change the number of grid points? That's a fascinating idea. I don't see why not. You could come up with ways you could put dynamics on those nodes. You could sort of have, deaths and births processes happening on these nodes, right? And then you can try to learn that process. I guess very sophisticated. And the more sophisticated you make, of course, the more data you need to train it. But this is what I mean is like, it's so early that there's like a massive, so here in this room, we can already think of like 10 great ideas, right? And this is another great idea. And yeah, so if you have enough data, you can learn these things and maybe it does better, right? So absolutely, yeah.
There were also multiple questions online, more on how that irregular graph, and Michael already asked about learning it. The question is how the nodes are getting connected in the irregular graph. How do you build it actually?
Well, this is just a sort of, I guess, oh, wait. It's based on the distance xi minus xj between the points on the grid. So, okay, you have some heuristic
positional parameters, basically. Mm-hmm. Okay, we have another question online from Jorge Amaya. The method presented requires an encoding and the decoding of the information before applying the GNN on the embedded space. What type of technique is used in the encoding decoding steps?
Yeah. So these two slides. So this is the encoding. So that is so the input is the information that you have, x and u. So actually here, you have x and you have so that's the position of that node, and you have the field values at that node and a history, and then of course the time point, if it's if it depends on the actual time point, and then the parameters. So that is going through some MLP, general MLP, to predict the initial embedding, and that's the same neural net for every node. Okay. Then comes the graph neural net, and then the decoder basically says, okay, so I have these, let's say here, I have, let's say, m iterations of this thing, So those are the m time points into the future. And then I do some, so node-wise, so for every node, I take these iterations of my graph neural net here, and I have some convolutional filter that I run over those feature values to then create my difference vectors D. Basically, the effect is it slightly adapts it and smooths it more or less, so we don't get very big jumps in the solution. Once we have the difference vectors, we then add them back to the fields. Now we have 10 predictions. We feed that back into the embedding phase, and then we repeat.
I have another slightly technical question. So you in your slide, you mentioned that you encode the condition, boundary conditions as some parameters in the encoder.
Yeah.
My question is, how do you hard limit that your results actually satisfies the boundary conditions? Is there such mechanism to do that?
Yeah, I think that's a good solution. That's a good question. Actually, I don't know precisely the answer to that. So there is, so the graph will have nodes on the boundaries, and you will set the value. Let's say if you have a U value, right? Then you know and your condition is my U value should have this value on the boundary. You just hard set these values at the boundary, and you will not change them or update them. And then that will be a fixed value, and then it will have an impact on the solution on the inside, right? And then for the derivatives, I'm not even sure we did that, but I guess you do have values for the derivatives as well, or at least approximations to the derivatives, and I guess you would have to set those to a fixed value. Periodic boundary conditions are easier, right? Because you just wrap this thing and then it's easier. And I think that's what we mostly did. But I think, again, there is still a lot of work to be done, which is how to for instance, if you have a symmetry, the symmetry might actually change the boundary condition as well. And the initial, well, it does change the initial condition, but also might also change the boundary condition. For instance, if you don't have periodic boundary conditions, but the fixed conditions, now the symmetry suddenly changes the boundaries as well. And so, what does that mean, right? It might create some very strange boundary condition. Is that still useful? Anyway, so there's lots of questions there still.
Pay attention to keep the microphone intact. I think we have one, and that goes back again to the creation of the data or the use of of what PDE you're using. Is it beneficial to use empirical measurements? Because in reality, you wouldn't necessarily know the actual underlying PDE. So
yeah,
maybe, but rather the problem, right?
I think that I feel is perhaps the most interesting direction. I actually started some time ago a collaboration with somebody in Leiden who had data of cells migrating through a worm. And so he looked at that and he says, this actually behaves a lot like a fluid, but I don't know what the PDE is for this fluid, right? And so there is some, microscopic theory, but at a microscopic level, it's best described by some kind of PDE, sort of smooth solution, like the emergent solution. But we don't know what the actual PDE is. Now, there's a beautiful application here, which is just feed it data and then train, give it, let's say, a very general PDE with lots of terms, higher order terms, a sparsity, inducing term which says, I don't want 1,000,000 derivatives, but I just want, a small one because I want my solution to be interpretable and not have too many terms. And then fit that to the data and then just backpropagate on the parameters of the PDE to find the actual PDE. That's a dream. I think it's not impossible. I think if you have a good data set, you might just rediscover Navier-Stokes equations, right? By just having lots of weather data, you might just rediscover Navier-Stokes. So that's certainly something that's high on my to-do list, but if somebody else does it first, that's fine too.
Excellent. Okay, thank you. Is there any additional? Yeah, that's one.
So one question would concern adding these symmetries to your PDEs, because I think it's also well known that conservation laws also are somewhat important symmetries. Is this yet incorporated with this framework, or is there still something to do to also have this
Yeah, it's
Because-
again, it's a great question because so Noether's theorem says that if you can express your symmetries in variational form, they will correspond to a conserved quantity. Now, people have used conserved quantities in solving PDEs, right? They basically made sure that, if there is something conserved, that the numerical solution exactly maintains that conserved quantity. For instance, an easy one is like the sort of symplectic integrators.
Yeah.
So I think there's still a lot to be discovered here, but I think sort of it feels like the dual flip side of the problem. So you can sort of embed the symmetries in it. And if you do it exactly, I think you will automatically have to maintain the conserved quantities up to maybe small errors that you're making. But then the question becomes whether it's not smarter to directly use the conserved quantities. And yeah, I don't know precisely the answer to that, but I feel that's a very interesting question to explore because these things are clearly related. Not every symmetry has a conserved quantity, I think, but certainly there's a class of symmetries that corresponds to conserved quantities and sort of, yeah.
Okay, and I would have a very technical question concerning this correspondence between, also to say at the very end where you talked about, so to say, using PDEs to improve neural networks. There was at the very end, a last slide, I think, an operator e to the e to some differential operator.
Yeah.
Yeah, something like this. Yeah, exactly.
Yeah,
so is this somehow? Is this? I think, as far as I know, to make sense of this operator here, you need somehow self-adjointness or things like that.
This
is very technical, so it's no.
I mean, for this operator, clearly it is, right?
It's a self-adjoint. Yeah, I think so. Yeah, but is this always the case to make sense of these things? Because I think functions of operators need somehow to make sense of these expressions, self-adjointness or properties like this.
Yeah, good point. So I guess here I assumed that, and sort of using. So another question is, if you use, I think if you use derivatives with constant coefficients, you probably have self-adjointness. If you have sort of these sequences, but then the coefficients start to depend on position, now you might not have it, but then you can, I guess, add the Hermitian conjugate to it, and then you make it self-adjoint, and then it should probably still do it. But actually, to be honest, it doesn't really matter, right? Because really, in the end, this is the solution, which is just a Green's function. You just need to be able to solve, the solution over a finite amount of time. And basically, you typically do this with the Green's function, and then you basically get some convolution. I sort of view this more as sort of a notation. Almost,
yeah, sure.
Right? Yeah, you have to sort of expand the exponent, and then and then you have to collect all the terms, and then you'll see that something actually happened in the argument. I mean, it's not really important.
A side note, yeah.
Okay, so we have 3 more questions online before we will then wrap up the call. Hope we can get there. Okay, so one is there a reason you don't include the physics loss in physics-informed neural networks?
The pins. I think it's actually quite related in the end. I mean, I could have talked about it at the introduction in some sense. So in pins, I don't think you actually try to numerically solve a PDE. It's more like you have a whole bunch of points in which you sort of want your, there's a certain PDE. You're trying to make a prediction, and that prediction needs to satisfy a PDE. So you sample a whole bunch of points, and you make sure that the constraints that are provided by the PDE are solved on those points. So I feel it's a slightly different application. It's like you're training a neural net to do something. You know that you want the solution to satisfy a certain PDE, and so you're trying to enforce this PDE as a constraint in some sense, or a regularization on your neural network. But the sort of core interest is your neural network. Here, the core interest is to actually numerically integrate the PDE. So it's sort of a slightly different view of a problem, I think. So here, the neural network tries to solve a PDE. There, the PDE regularizes a neural network. But yeah, that's also, of course, related in an interesting way. Yeah.
Okay, good. Okay. One question more on the procedure here seems to be depending on the encoding. Is it possible to proceed without the encoding step, and how necessary does the encoding step?
Yeah, that's sort of an ablation study question, and I don't know. I don't think we did that ablation, or maybe, I mean, you don't know. Maybe we started without doing it. It didn't work. Then we piled a whole bunch of other things on it. Then we forgot to test whether it actually was necessary. I mean, there's so many things you can try. So of course, I don't know the actual answer whether it's still necessary. I do think it does make sense, right? Because you want some initial embedding for your GNN to work on. I think the GNN could also work on just the field variables and the positions. And that way the transformations could be absorbed in the GNN updates in some sense. So I think it will work. If you can make it work better, I don't know.
Okay, and final question, have you tried using edge features? It seems natural to encode the parameters of the PDE on the edges rather than the nodes, thinking of nodes as values of the fields and the PDEs as interactions.
The edge feature. So you mean like in this GNN, let's see if you can find the GNN update here. Explicitly adding edge features. So then what would these edge features be in this case, apart from the things that we already, because xi minus xj in some sense is an edge feature. And these difference vectors are also edge features if you wish. So is there any other edge features that we would need to take into account?
That's a good question. Thinking of nodes as values of the fields, hence it would be the interaction side on the edges.
Yeah, but if you think, so the interactions would be the derivatives, right? So because everything depends on derivatives. And if you look at this, so we have the difference vector and we have of the fields and we have the difference vectors of the x. So the ratio of these two are actual derivatives. And so in that sense, we do take derivatives implicitly into account.
So
between two.
It wouldn't make a difference, right? It's
I
just
never
a
know.
permutation of
I don't quite know what the person was suggesting to add in addition to this. I don't think we have much more information than derivatives and differences on the edges that we can add. But if, I mean, clearly if there is additional information, pile it on, right? I mean, it's just a neural net. It can decide to ignore it.
Yeah.
Yeah. But at this point, I couldn't think of anything else, basically.
Excellent. Okay. All right. I think we have had very interesting 1.5 hours. Thank you so much for your kind talk. Thank you all. Thanks also for the questions in the room and online. And thanks everybody. And have a great day. Bye-bye.